Hello, everyone. Thank you very much for joining us today. We are excited to have this live session with you, and I'm going to hand this over to Chris. My name is Matthew, and I'll be choosing questions from the chat and from emails, and we're glad to have you with us today.
Okay, welcome everyone. Another large crowd online live, and a lot of questions mailed in too. So we'll get right to it. Floor is open for questions about astronomy, any topic.
Okay, Chris, the first question is from Christina, who sent an email asking about craters on planets and the moon. So she understands that generally, if there are lots of craters on a surface, it means that the surface is very old, and if there are few, it means young. Is this referring to the solar system, or is this generally the same around the universe?
That's a good question. So I'll sort of answer it as two different questions. I'll answer what cratering tells us in the solar system, and then I'll answer what is really a second question about cratering in the universe. So in the solar system, there's debris left over from the formation of the solar system. It's a sort of power law or logarithmic distribution of debris where there are very few large chunks and orders of magnitude more very small chunks. So space rocks bigger than sort of asteroid size, kilometer or larger, are very, very rare. Space rocks that are centimeters in size are quite common. And this material is generally in the equatorial plane or the ecliptic plane of the solar system, the flattened disk. And it travels through interplanetary space, and it impacts objects in the solar system. And it's random, so the arrival rate is random. A planet with an atmosphere, generally the atmosphere protects the planet from impacts, and so there is no evidence of the cratering, or only evidence of the very largest objects that impact. The gas giant planets, of course, objects will plow into them, debris plows into them, and it burns up in their atmospheres, and their rocky cores are very deep in the planet, and nobody knows if they even make a crater. But the terrestrial planets have a cratering record. Venus has a thick atmosphere, and so probably will have the least number of craters because its atmosphere will burn up everything, and volcanism has resurfaced the planet heavily, especially about 600 million years ago. The Earth is a sort of intermediate case. We have an atmosphere, and so we do have evidence of craters, but really only the big ones. All the small stuff burns up in the atmosphere. And also the Earth is a tectonically active planet with water and erosion, and so evidence of craters is removed over time. And so there are not many big craters on the Earth's surface. The idea of dating a surface by counting craters really only applies to objects without a substantial atmosphere. And the moon is the perfect example, because the moon is a twin, is close to the Earth in space, and so it's received the same type of objects impacting it as the Earth has. So it's like looking in a mirror in terms of debris coming in, but it has no atmosphere to burn them up. So the craters just present perfectly as a history of cratering over 4.5 billion years. And so you can age date a surface by the number of craters, because the cratering rate has declined over time as the debris in the solar system was mopped up from the first 500 million years or so, and the cratering rate is lowered to a sort of low but steady rate. Mars is another case where people have used the cratering count, because the atmosphere is 1% of the thickness of the Earth, so most get through and leave impact signatures. And so people have age dated surfaces using craters. And the idea is, when volcanism kicks in or there's tectonic activity, that will cover the surface. And so the surface gets wiped clean of craters, and then the new craters start impacting. And so there will be obviously fewer crater impacts on a young surface than an old surface. So that's the theory. As for cratering in the universe as a general phenomenon, that's a good question, because we assume, because our solar system is not unique, because we know of many exoplanet systems, and we found many terrestrial planets, that those solar systems will also have debris. They won't form perfectly where all the mass either goes into the central star or a set of planets around that star. These processes are inefficient, so there will be rocky debris left over. The asteroid belt, of course, is the source of a large amount of the rocky debris in the present solar system. And so, yes, we would assume that the material to cause cratering exists in all the exoplanet systems we found so far. And if we had terrestrial exoplanets with thin atmospheres, they would show evidence of that cratering. And it's very unlikely we'll have enough detailed information to do that kind of work in another solar system in the foreseeable future.
Thank you very much. The next question is from one of our live participants who would like to know about dark, let's see, as light is a source of energy, could darkness be the source of energy? And is this related to dark energy?
Darkness being the absence of light or electromagnetic radiation, it's not an intrinsic source of energy necessarily. Dark energy, however, does exist in the vacuum of space, independent of any other matter or radiation in the space. So dark energy is a property of space-time as far as we can tell, and so it does not depend on radiation, and so it's independent of whether there's light or darkness in that space. So it's a good question because it shows that dark energy is just a fundamentally different entity from radiation, from whence we get light and darkness.
Layla sent an email and she says it's been her childhood dream to study astronomy. She believes she's probably too old to become a professional astronomer, but what is the best way to contribute to astronomy or to become a good amateur astronomer?
Well, that's a good question, and there's a good answer because there are many ways to contribute or partake in astronomy without being a professional astronomer. The two main ways are, yes, indeed, to become an amateur astronomer, and the modern world of small telescopes has advanced quite a long way with cheaper plastics and materials, with the automated technology of what are called go-to telescopes, where you just punch in your sources or have a list of sources, and they sort of calibrate their position on the sky and go automatically there. So you don't actually have to know your way around the sky. So the bar is lowered both in cost, the ease of use of the telescopes, and their capabilities, because they'll probably be on the internet and have all the information you need about the objects you're studying. So amateur astronomy has, in a sense, got easier. About 1 million telescopes a year are sold to amateur astronomers, as far as I can tell. The median price is $400 or $500. But for $200 or $300, you can get a decent starter telescope. $400 or $500, maybe $600 will get you a nice one, a really nice one. You do need to be in a decently dark place, or at least have access to a dark-ish sky to see, to get full benefit out of the night sky. And I'll also point out that a good set of binoculars, high optical quality binoculars, get you very close to the sort of low-end range of optical amateur astronomer telescopes. You can do a lot with binoculars too. So I would recommend that. Almost all towns of any decent size have an amateur astronomy club. There's an organization called the Astronomical League that is the umbrella organization for amateur astronomy clubs. So if you go to their website, you can search by state, by zip code probably, and find one that's near you. They are very friendly. They love to have new members, I'm sure. They have meetings, and you'll find one, hopefully, that's active. That's one way. And the other way to contribute to astronomy is citizen science. If you go to the Zooniverse website, zooniverse.org, that is the umbrella organization now of citizen science projects, and its origination was the Galaxy Zoo, which was a galaxy classification project. And the point of citizen science is to have members of the public, not trained professional scientists, doing scientifically meaningful tasks involving real research level astronomical data. And there's a range of them. It can anything from exoplanet hunting to galaxy classification to search for extraterrestrial intelligence signals to looking for gravity wave signals in LIGO data. Some of these are needle in a haystack type activities, and some of them are more focused, structured activities based on a scientific idea. But there's tons out there, so you are strongly encouraged to jump right in. So, long pause.
Oh, sorry about that. My microphone didn't unmute. The next question is from Richard Elkins, who's on with us live, who would like to know if you can please explain the recent experimental results from the University of Bonn regarding cosmological anisotropy.
Right. This came up last week, but I'll address it again. It's still in the news, and it's a major issue. This research group is an international research group, has used X-ray data on clusters of galaxies. So we can measure the properties of clusters of galaxies out to billions of light years away. And some of the properties of clusters of galaxies are sort of standardized in the sense of there's a relationship between the mass and the X-ray temperature of a cluster of galaxies, and also how they affect the microwave background. So X-ray emitting clusters of galaxies are important cosmological tools because they can be calibrated to measure properties of the universe, such as the distance out to a particular redshift or the mass of a particular cluster that's forming at a particular redshift. And the short story is that this survey, which involved clusters in all different directions in the sky, seemed to find an anisotropy. Anisotropy is when the universe is different in one direction than the other. And it's a foundational principle of cosmology. In fact, it's an assumption built into modern cosmology that the universe is homogeneous and isotropic. Homogeneous means the same at every location, and isotropic means the same in every direction. In other words, if you point your telescope far away, far from the Milky Way in any direction, you see roughly the same galaxies, roughly the same objects. Nothing substantial varies across the sky. And they claim to have seen significant variations in these core properties of X-ray clusters between different locations in the sky. If true, it's a major result. It's an extremely uncomfortable result for cosmology because it violates a core principle of cosmology. And I would say that in the history of modern cosmology, these are difficult experiments, difficult measurements. There are errors of various kinds, random and systematic. And astronomers tend to be fairly skeptical of such claims, not because the people who did it were careless or didn't know what they were doing, but just because the signals they're working with are very subtle, and we don't fully understand the astrophysics of rich clusters of galaxies. We use them as well as we can, but we don't fully understand everything. So my judgment at this point would be interesting. Let's see more, or let's have it corroborated with a different method. I don't think cosmology is going to crumble because of this, but if it stands, then it will actually be kind of an important result.
Thank you very much. All right, the next question is from Seamus, who's on with us live. What impact will the Starlink satellites have on astronomy, and what impact will these small satellites have on orbital space debris?
Right, the Starlink satellites, for people who don't know, is a set of it's a telecommunications project run by SpaceX, Elon Musk's private space company. So Starlink it has a noble goal. The goal is as people may or may not know, everything runs on the internet, but there is a good chunk of, especially the developing world, 1 billion and a half people that don't have access to high-speed internet or wireless internet. And that's a limiting factor in economic growth and their ability to contribute to their society, and in their isolation when they live in a remote rural part, say, of Asia or Africa. So the Starlink project has the goal of launching a set of small satellites, microsatellites, they're not quite nanosats, but small satellites that will facilitate a web, a global grid of telecommunications and wireless internet with a very dense sampling. So you will not be able to be anywhere on the Earth that doesn't have access to these satellites. They're going to be put in low Earth orbit because that reduces the power requirement on their transmitters. But low Earth orbit also means their orbits degrade over time. So this constellation, this fleet of small satellites, is designed to need hundreds and actually thousands of satellites to operate, with the knowledge that they're going to continually be burning up in the Earth's atmosphere. They burn up harmlessly in the Earth's atmosphere and need to be replenished. The problem is that even though the satellites are small, they're reflective, they're at a fairly low altitude, a very low Earth orbit, and to the most sensitive telescopes that astronomers have, they're quite visible. And they're particularly visible, as you might imagine, near sunset and sunrise, when the sun is essentially just below the horizon, glinting off them. And so these are times when astronomers would be working because the sun has set, but sun's radiation is bouncing off them. And it is easily detectable to a large telescope, even to a medium-sized telescope. So astronomers have raised the alarm, and I was at a session of the American Astronomical Society meeting in Honolulu in January where there was a whole session on the threat to astronomy. Actually, not just optical, radio astronomy is threatened by this at some level too because of the transmitters in these satellites. And there was a representative, pretty senior representative of SpaceX, wasn't Elon Musk, in the room. So SpaceX claimed to be sensitive to astronomers' concerns, and they have tried to use a matte black, different type of coating on their next generation of satellites to reduce their reflectivity. And it's not clear that that's made that much of a difference. It's a little better, but not hugely better. The concern is that their goal is to have more than 10,000, I think it's closer to 20,000 of these satellites when they reach full capability. And the people simulating what the upcoming survey telescopes, like the Large Synoptic Survey Telescope, a huge nationally funded project to look at the southern sky, essentially to Hubble depth every night, that telescope will see these satellites. They will actually, mess up substantial parts of almost every frame that telescope takes. So astronomers are quite nervous about light pollution, that's what this is. And there are, slightly awkward negotiations and conversations going on with SpaceX about this, and they're driven, with some altruistic motive for their original project, but they're driven by the profit motive as well. So it's not clear how this will shake down.
All right, thank you very much, Chris. The next question is from Sakathram, who's on with us live, who would like to know if a star can turn into a planet or vice versa.
They're typically different. The definitions of a star is a gravitational, a sort of self-contained gravitational object made of gas, whose mass is sufficient for the central temperature to be above the level where fusion can occur. And the simplest, the feeblest form of fusion is deuterium fusion, and that's a couple of million Kelvin. Hydrogen fusion to helium, like the sun does, takes about 5 million Kelvin. So that's the definition of a star. And any gas ball that has gravity that doesn't reach a central temperature high enough for fusion to occur is not a star. A planet, however, is something different. A planet is something that forms around a star. So the real difference is just a definitional one, that when a rotating gas cloud collapses to form a central object, that central object, if it emits energy, is a star. And rocky and gaseous debris that aggregate by gravity around the central object are by definition planets. Or if they're very small, they could be called asteroids. Or if they're very far out and in a spherical region, they're called comets. So these are the sort of definitional things that astronomers sort of have baked into their thinking about objects in space. But there is a dramatic difference between a planet and a star.
All right, the next question is from HN, who's on with us live, who'd like to know if what's the current thinking about Betelgeuse and or Betelgeuse? Are we going to get a supernova?
So Betelgeuse is changing in its behavior, and the most recent data from the last few weeks has it sort of settling down. So Betelgeuse was into an active phase, varying its light output in a way that indicated to many astronomers that it was potentially nearing the end of its life, going into, because at the end of a star's life, as it consumes the last of its nuclear fuel, it will reconfigure by gravity. The pressure balance is broken in the star when the fuel is consumed, so it has to reconfigure itself, ignite a new nuclear fuel, and if no nuclear fuel is available, that's the end of the life of the star. And there was a hint, or there were hints, significant hints, that Betelgeuse was entering this final phase, its death throes, if you like. It seems to have settled down recently. It's remarkable, apart from anything else, that a star, a huge object, vast object far away, can actually change its behavior on such short timescales so that people can notice it from month to month and see differences. So it's being very heavily monitored, of course. It's a big, bright star. It's physically large, giant, and it's bright, so anyone can pretty much observe it with a small telescope. So it's getting plenty of attention. seems to be quiet right now, and nobody really knows what's to come. The data is not good enough to say for sure that it's about to die or when it might be about to die. It's late in its life in general terms, but that in astronomy could mean it's hundreds of thousands or tens of thousands of years away from the end of its life. We simply don't know.
The next question is from a live participant who would like to know the concept of right ascension and declination are not very clear to me. Could you please explain what they mean?
Okay, these are the astronomers' coordinate systems, and the coordinate systems for finding an object on the sky for astronomers, professional or amateurs, are based on, basically you need two orthogonal coordinates to point to any object on the celestial sphere. So any object in the night sky can be defined essentially by two angles. The simplest, the most intuitive angles are in the altitude azimuth system. And that would be if you just go out to a place where you can see your entire horizon at night. The altitude is literally how many degrees above the horizon the object you're looking at is. And the azimuth would be how many degrees around the horizon is it from some cardinal point like due north or due east. So that's very intuitively obvious that any place you could point to in the night sky has those two angles, which are easy to understand. The astronomers use a different coordinate system. It still involves two angles, but it's referenced to the equatorial the equator of the Earth, because the Earth is a spinning object. And so as the night sky rotates overhead, it rotates with an angle that depends on your distance from the equator. And so if you were standing at the equator, the night sky stars rise directly out of the east and set into the west. And if you're at the pole, the stars essentially do circular orbits about a point over your head, which is the north celestial pole. Right ascension and declination are the two angles that astronomers use in this equatorial system, as it's called, because it relates to the equator of the Earth projected out into space. Right ascension is measured in time units, so the range goes from 0 to 24 hours, because that would represent the entire sky as it rotates. The night sky rotates every 24 hours. But of course, you can convert easily the hours into an angle, because you've got 360 degrees through 24 hours, so every hour is 15 degrees of angle. And then declination is the angle above or below the extension of the equator of the Earth projected into the night sky. So northern or positive declinations are angles above the equator, and negative or southern declinations are angles below the equator of the Earth. And that's a system that all major research telescopes use.
Thank you. The next question is from PT Cruiser, who's on with us live, who would like to know what effects, what would the effects be on Earth from our planet being hit by a gamma ray burst?
Well, they could be dramatic. They could be terrible. Gamma ray bursts are essentially the most powerful explosions known in the universe. Some people call them hypernovae. They're not exactly the same thing, but these are massive stars that die with a catastrophic explosion that exceeds the energy of a typical supernova. Because the stars are spinning, the blast wave, or a lot of the projected energy, radiation, and plasma comes out along the poles. And so a gamma ray burst is a jet or a beamed amount of radiation, a phenomenal amount of radiation. In their moment of their explosion, a gamma ray burst exceeds the energy of an entire galaxy by some factor. And a lot of it's coming out at very high energies. And so at the moment of their detonation, any gamma ray burst is brighter than all other gamma ray sources in the universe. So the problem comes with that amount of energy is, what if you happen to be in the line of sight of this jet? Now the jet is quite narrow. It has an opening angle of a few degrees, maybe 5 degrees. So the thing would have to be detonating and pointing at you quite accurately for you to be in the line of sight. The good news is that gamma ray bursts are very rare, because only the most massive stars, or star in a binary system where one of the components is massive, can die this way. And massive stars that massive are rare statistically. Less than 1 in 1,000, maybe 1 in 10,000 stars are like this. So the nearest star that could die as a gamma ray burst is going to be hundreds of light years away. However, even at a distance of a couple hundred light years, a gamma ray burst that happened to be pointed at us as it went off would cause problems. It would ablate the Earth's atmosphere, probably destroy the ozone layer and our protective shield against high energy radiation, and really cause a sort of ecological crash of the biosphere. The distance at which we start to be safe is probably about 1,000 or a few thousand light years. And because gamma ray bursts are rare objects, and because we know that opening angle, people have tried to work out what are the odds it will happen, or on how often does it happen. Given that it will happen and it could be pointed at the Earth, what's the incidence rate? That's a pretty uncertain calculation, but the best numbers I've read say that it happens about once in the sense that will impact the Earth at some distance where it'll make some damage to the Earth once every 100 million or 200 million years. In other words, not really something to lose sleep over.
All right, the next question is from one of our live viewers, and they would like to know about comets. Where do they come from, and really more, how do comets form in the outer reaches of the solar system? Like, do they start as small and like build up around a core? Like, how does that process work?
Yeah, there are still some uncertainties about comet formation, just as there are about solar system formation. But if we look at the comet cloud, the Oort cloud, named after Jan Oort, a famous Dutch astronomer of the 20th century, he actually lived well into his 90s, and I think he was active doing research into his 90s. Quite amazing guy. So the Oort cloud is at very large distances from the Earth. It's a spherical cloud, whereas the planets are in a plane of a disk. The Oort cloud has comets that go out to probably tens of thousands of astronomical units. Generally 50,000 is the typical number people say. Now remember, the orbit of Neptune and Uranus, those are about 40 astronomical units. So we're talking about a cloud that's 1,000 times more diffuse than the planets, the outermost planets. It's spherical, and these objects, are estimated to be 1 trillion of them, are small rock and ice balls, up to a few kilometers in size, but typically more like hundreds of meters in size, that spend most of their time in their highly elliptical orbits very far from the sun, and so they're in the deep freeze of space. And the idea is that they're a sort of frozen relic of the very formation of the solar system, because the solar system, before it collapsed to form the sun and planets, was a nearly spherical cloud of gas and dust that collapsed either spontaneously or due to influence of a nearby explosion that might have triggered it into collapse. And so these comets, which are astrophysically very small objects, just condensed or formed by gravity processes throughout the large spherical cloud as the core of the cloud was collapsing more rapidly to form a star and the leftover planets. So we think the comets are primordial, they're primeval, they date back to the very beginning of the solar system. Their spherical geometry and their large distribution in space reflects the initial size of the cloud that formed the solar system, which is why they're fascinating objects, because when they do occasionally come into the inner solar system or close to the Earth, or very occasionally we get to take a sample of them and send a spacecraft there, that's a really good way of doing archaeology of the very early history of the solar system.
Okay, the next question is from Freezing Silver, who is on with us live, who would like to know if you can please explain the different kinds of novas and supernovas, and specifically they'd like to know what a type 1a supernova is and why they're important.
Right. So the basic difference between, so this is like two questions, I'll answer it as if it was two questions. What's the difference between a nova and a supernova? Good question. The word is from Latin. It means new star. So a nova is a new star and a supernova is a super new star. And these terms date back to antiquity, obviously the Greeks and the Romans and so on. And people had seen what they call guest stars appear in the sky, so stars that just appeared where they hadn't been there before. And these were a mixture of nova and supernova events, but the astrophysics of them was not understood until the last century. So a nova is basically an evolved star, an old, probably more massive than the sun star, which becomes highly unstable in its later life. And it can set up episodic pulsations, which have a long time scale, and it will periodically brighten and dim. And so there are recurring novae, which do this. They, because of their instability and the change in their fusion rate, they can brighten or dim an enormous factor by factors of 100. And that can easily take them from being a star too faint for the naked eye to see to one that the naked eye can see. And so those are the ones we've seen through history. And we've learned a lot about the late stages of stars' lives and evolution and their energy processes by studying novae, because these are stars that are creating heavy elements as we speak. Not all of the novae are regular. Often their variations are irregular or seemingly random. And occasionally there are novae that we haven't seen recur. So there are novae that have recurred historically with gaps between their outbursts of maybe years or decades or hundreds of years in the historical record. But there are some novae that have only been seen to go bright once, and they've never been seen to recur bright. But we think we understand them. They're individual evolved stars. A supernova is something entirely different. It is a massive star near the end of its life. So what are the differences between the different supernova types? Basically, astronomers have developed a finer gradation of this, but in simple terms, there are two types of supernovae, the type 1 and the type 2. The type 1 supernovae are supernovae that form in a binary system, where because of the mass transfer from one star to the other, the more massive star has mass put onto it such that it just exceeds what's called the Chandrasekhar limit, and that's enough to cause it to detonate as a supernova. And now the fact that the star dies and explodes in a binary system is important because it's in a binary system. This is a very regulated process. It's just getting mass poured onto it slowly from a companion till just the point where it will detonate. And it turns out that the energy released in those detonations is very uniform. It doesn't vary by more than 10 or 15% from one supernova to the other. And so these type of supernovae in binary systems, the type 1s, have been extremely useful tools for astronomers, because in that detonation and brightening, a single star can brighten to the brightness of an entire galaxy. So it's literally brightening by factors of billions. And that brightening is well calibrated, it's well understood. And so we can use how bright a supernova appears to say its distance. And so supernovae of the type 1 have been used to estimate distances in the universe to very large distances, billions of light years. And a lot of cosmology has been done with type 1 supernovae. So they're important for that reason. A type 2 supernova is a single massive evolved star that dies, that reaches the end of its life, exhausts its fuel supplies, and has a core collapse that then explodes as a supernova, leaving behind probably a black hole or possibly a neutron star. The type 2 supernova doesn't have a well-calibrated luminosity because these are stars of different masses. They're not a binary system. They're just living their own lives and dying at the end of their life and having consumed all their nuclear fuel. And they actually tend to be, because they can be very massive stars, they are more luminous than a type 1 supernova. They're some of the most luminous events in the universe. The average rate of supernova in a galaxy like the Milky Way of either type is about 1 per 50 or 100 years. So we are actually long overdue, because the last supernova in our galaxy was in 1604, observed by Kepler, and we haven't had one since.
All right, the next question is from Tony Stark, who I would think would already know the answer to this. But what is the most accurate method for calculating the distance to stars?
Absolutely, the most accurate method is geometry, so trigonometry, so parallax, because space-time is flat. We've had microwave background radiations to show us that our space-time is beautifully Euclidean, and so you can apply simple geometry. And the parallax method is simple and very reliable. It requires really good precision of angular measurement, and then with the Gaia satellite, the European space mission that was very successful and took data for on actually close to 1 billion stars in the Milky Way, but measured accurate positions for tens of millions of them. That's the biggest treasure trove we have of stellar distances. And so we've been able to measure, Gaia took our ability to measure star distances by parallax up from stars of a few hundred light years or a few hundred parsecs up to a few thousand parsecs. A significant chunk of the Milky Way has been mapped out with exquisite positional accuracy. And those distances, of course, when they're measured that well for that many stars, have enabled a whole set of statistical projects on astrophysics. So although it's a kind of a humble and fundamental thing to do to measure the distance to a star by the parallax method, it's very classical astronomy, it's actually enabled some very remarkable studies in the last decade or so. Aha, long pause.
Oh, sorry, this mute button is kind of sticky. My apologies. The next question is from Parth, who's on with us live, who would like to know what counts as extraterrestrial life. Can proteins of unknown origin be counted as potentially extraterrestrial?
I think the life boundary, which is still an issue that biologists will debate, I think proteins lie comfortably on the non-life side of that boundary, because proteins are, molecules that have clear function in a biological organism, but they don't function autonomously. They have no autonomous capabilities. They are not capable, no matter how many proteins you had in an aqueous medium or in one place, they can't evolve, they can't adapt, they can't respond to their environment. They're expressing something in genetic material in a living organism. So proteins, no, would not be considered living material if we found them elsewhere. They would be considered to have arisen naturally just by molecules combining to become more complex, and that's about it. The interesting distinction, made very pertinent by the fact that we're living through a pandemic right now, is the virus and bacteria division. And biologists don't fully agree on this. I'm not a biologist, but I ask them these kind of questions. And viruses, of course, are, they have genetic material and they can replicate, but they don't exist autonomously. They depend on a cell. They depend on bacteria or a living cell to function. So on their own, they are not able to survive. And so most biologists put viruses on the non-life side of that boundary too. But it's a little less clear, because in a living system, the role of viruses and bacteria they're equally essential at some level. They're commensal. They depend on each other at some level. So they've co-evolved. And this is just one example of why definition of life is such a tricky topic.
The next question is from Julie, who's on with us live, who would like to know, when an object falls into a supermassive black hole at the center of a galaxy, does it pull in more mass near it to the black hole because of its own gravity? So like why, I mean, at some level, why isn't the entire galaxy just sucked into a black hole when something falls into a black hole at the center?
Right, that's a good question. So we'll take our galaxy. It doesn't have a vast black hole. 4 million times the mass of the sun is quite a modest supermassive black hole. It's pretty beefy, and we've studied it up close, so we can talk about it quite well. The galaxy's black holes, all of them, including ours, are material is falling in either as dust particles or gas particles, that is single molecules of gas, or as whole stars occasionally. So black holes can eat whole stars. Now the gravity of a single star, of course, is millions of times less than the gravity of the black hole that's pulling it in. And so really when a star is pulled in by a black hole, it's just the star. It doesn't bring with it a lot of other stuff because the star's gravity is so small compared to the black hole's gravity. As for why the black hole at the center of a galaxy that is pretty large, millions of times the mass of the sun, doesn't sort of consume the whole galaxy or just vacuum up a lot of stuff, there's a couple of answers to that. I mean, one is that the center of a galaxy and the black hole itself is very small. And the black hole at the center of our galaxy is order solar system size. And the galaxy itself, the whole galaxy, is 100,000 light years across, which is hundreds of millions of times bigger than the solar system. So the black hole exists on a very, very small scale at the center of a galaxy. And as a fraction of the mass of the galaxy, it's really quite small. So our galaxy, it depends whether you include the dark matter or not, but it has 300 or 400 billion stars. So you could say that our galaxy is of order, 400 billion times the mass of the sun. And the central black hole is 4 million solar masses. So the black hole is a tiny, tiny fraction of the galaxy's mass. So it really doesn't dominate the motions and behavior of the entire galaxy that it's in, because it's small and because it's a tiny fraction of the galaxy's mass. So in truth, the black holes at the center of galaxies, big or small, however big they are, really only affect what's going on very near the center, usually within a few light years or maybe a dozen light years.
All right, the next question is from one of our live viewers who would like to know, excuse me, if a Dyson sphere is possible for us to build, and if another alien species has built one around a star, how would we detect it?
So the first question to answer is, what is a Dyson sphere? So Freeman Dyson, this is very timely because Freeman Dyson died just, I think, last month at the age of 95. He's a very eminent physicist that worked at the Institute for Advanced Studies, the place that Einstein spent the last 20 years of his life. Actually, his office was just down the hall from Einstein's old office, and he knew Einstein because, of course, he's an old guy and was there with Einstein too. Freeman Dyson was a great and original thinker in astrophysics, and he made many, many contributions. The Dyson sphere concept is just one of them. He speculated about life in the universe, and his interests were very broad, and he just imagined that a civilization more advanced than us would want to capture more of their star's energy and radiation to run their civilization than we do. So the Earth intercepts at its distance from the sun about 1/1000th of the sun's radiation, and we very inefficiently, especially since we don't have much solar power, utilize some of that information, some of that energy. So his idea is that if you were going to step up enormously from our capability, you would obviously want not only to use all the energy that your planet intercepted, that landed on your planet, but actually, why not go up that factor of 1 billion and intercept the entire star's energy? And how would you do that? Well, you'd build a physical structure, a construction, a shell around the star, close to the star, that would trap the energy, store it somehow, and then ideally just re-radiate it or beam it, transmit it to the home planet that was still in its original location. So the Dyson sphere is, a very clever idea of how a civilization might build something around their star that would give them 1 billion times more energy than they were naturally going to get coming through space. Clever idea. Is it physically possible? Yes, it's physically possible. It's not going to be a solid thing because the dynamical forces on such a construction, which would have to be rotating, would rip it apart. So it'll be a sort of skeletal structure that wouldn't really, in the end, intercept all the star's radiation, but a good fraction of it, of course. So the second question, it's a really distinct question, is given the possibility of Dyson spheres as signatures of extraterrestrial civilizations, how would you detect a Dyson sphere? How would you even know one existed? And that's an interesting question that the people who do SETI, Search for Extraterrestrial Intelligence, have considered, they've thought about for a while. People who do SETI also are honest enough to say that their acronym is not really very smart because nobody knows how to search for intelligence out there in the universe because we don't even really know how to define it very well, and that's not even what they're doing. Really, SETI should be abbreviated SETT, the Search for Extraterrestrial Technology, and a Dyson sphere is a technology we might detect. The way we would detect it is by the fact that energy storage and transmission is never perfectly efficient. And so any energy trapping sphere would by thermodynamic principles have to radiate energy in the infrared. It wouldn't be perfectly efficient. There's no perfectly efficient energy trapping technology. The structure itself would heat up at some level and radiate in the infrared. So in principle, the way you detect a civilization that may be trapping radiation from their star is by looking for thermal or infrared excess radiation from that star that you wouldn't normally expect, because stars don't tend to emit infrared radiation. They're black body emitters with a very clear energy spectrum based on their temperature. And so that's the signature of a Dyson sphere in principle. And that sounds simple. Look for an infrared excess around a star that shouldn't have an infrared excess. But it's not simple in practice. It's not simple because this infrared excess might be quite a subtle signature, really a modest signature, not a good fraction of the total energy of the star. And second, there are reasons why stars emit infrared excess that are nothing to do with extraterrestrial civilizations. For example, if there's a residue dust and gas cloud around the star from its formation, or just leftover material that stayed near the star, that material will be heated up by the stellar radiation and radiate in the infrared, and so it will look just like a Dyson sphere. There have been a couple of papers that I'm aware of that looked for Dyson sphere signatures by infrared excess, and the results are always ambiguous, and no one's claimed a detection at the moment.
The next question is from Pashupati, who sent an email. What is the best explanation right now for either the loss of the magnetic field on Mars or the lack of magnetic field on Mars?
The best explanation is actually a combination. It's the fact that the Mars, even early in its history, never had much of a magnetic field, and also that its magnetic field may well have decayed over time. So if we look at Mars, its magnetic field is not zero. The Moon has no magnetic field, for example, but it's a lot less than the Earth or Venus. The strength of a planet's magnetic field really depends on two things. It depends basically on their mass, because the more massive terrestrial planets will have metals that sink to the surface, sink from the surface to the core as they form. And if they're massive enough, the energy or the temperature of the core from radioactive heating or just pressure within the rock will create a magma layer, either around a solid core or perhaps the entire interior is liquid. And it's the rotation of the planet and that liquid metallic core through a dynamo effect that builds the magnetic field. So the Earth and Venus have strong magnetic fields. Mars is substantially smaller than the Earth, and so if it has a metal core, it's a much smaller core, and it may and would not have generated a strong magnetic field to start with. Now, Mars has had tectonic activity, so it's not that Mars is geologically dead, and it's not that Mars couldn't have had a dynamo effect to build a magnetic field. So people do think Mars did have a significant magnetic field. But as Mars becomes a dead planet, and Mars is largely geologically dead at the moment, that magnetic field that it had would degrade over time. And so it's some combination of a initially weak magnetic field and some loss of the magnetic field over billions of years.
The next question is from Russell, who sent an email. And Russell says, when I'm looking at the sky, I often wonder which objects are planets and which ones are stars. How can I tell the difference between a planet and a star?
The easy way, without a chart or some guide to help you, is that the word planet comes from a Greek word planeta, which means wanderer. And so to the Greeks and the Romans and the first people who looked systematically at the night sky, the planets are objects that move relative to the stars. So that doesn't tell you on a particular night which is a planet or a star. But if you were to notice a bright object in the sky and you wondered whether it's a planet or a star, you could just sketch the object and what's near it, the stars that are near it, and the pattern, and go out the next few nights and see if it moves. You probably need a week or so rather than a few nights. And if it moves, then it's a planet, because the stars are very far away. They don't change their relative positions on the sky. And the planets are nearby in the solar system, and they move at different speeds around the sun. And so they do change their position in the sky. So one way to tell if something that you think might be a planet is to go and observe it, just see where it is relative to nearby stars for a period of time. The second way, of course, is that planets, because they are nearby, stars are, of course, much larger than planets, but the stars you see are millions, hundreds of millions of times further away than the nearby planets. So the planets appear physically larger. They have a larger angular size. And that means they don't twinkle. So in simple terms, stars twinkle because of the effects of the Earth's atmosphere sort of blurring out their light, even though the stars are physically far away and very small appearing. Planets are closer, and so they don't appear twinkling. You can't really make out features on the planet, but when you stare at them, their brightness doesn't seem to vary. They don't seem to shimmer or move around or twinkle. So that's another way to tell. Now that doesn't work for that method only works for Venus and Mars and Jupiter. Probably it doesn't work for all the planets. And then the third thing you would look for is where in the sky they are. Because the planets are all in the equatorial plane of the solar system, they're very close to the ecliptic. The ecliptic is the line that the sun, so just point to the sun and then see the path that the Earth takes around the sun, or that the sun takes in the sky. That's the ecliptic. And if you look, and the moon also is close to the ecliptic. We're tilted only by 4 degrees from the ecliptic. So if you notice where the sun and the moon are in the sky, or where they've traveled in the sky, the planets are always in that same line. They're along the ecliptic or close to it. So that's why you can often see the planets close. You can't see them when they're that close to the sun, but they're close to where the sun was before it set, and they're often close to the moon because the moon's also in the ecliptic. So those are the 3 ways to tell.
The next question is from Crystal740, who asks, will the Mars 2020 rover be postponed?
Yes, the Mars 2020 rover has been postponed to 2022, and there's a date, but I'm not sure I believe it. So we'll just settle for saying that it is postponed. NASA's had, of course, there have been hiccups with a number of their programs. With the pandemic, NASA, the federal employees and subcontractors, people who prepare these missions and do the work, a lot of them are on lockdown. A lot of them are not able to work in their, close confines of their labs, where a lot of people have to work close together. And so a lot of construction work on space missions, including James Webb, has been put on hold, and Mars 2020 is in that boat. It will go. And of course, unlike James Webb, which is in a Lagrange point orbit where you can launch at any time, to get to Mars in the most efficient way, there are launch windows separated by every 1.5 years or so. So when you slip a launch date, you can't just slip it by a few months. You have to slip it by more than a year, a little under 2 years. So 2020 turned into 2022.
The next question is from Akshita, who's on with us live, who asks, I've heard that stars rotate at different rates throughout the star. The sun rotates differently in the middle than at its poles. Does the size of the star impact the way each segment of a star rotates?
Yes, that's a good question, because stars are not solid objects. So they have what's called differential rotation, which means that the equatorial regions rotate faster than the high latitudes or the polar regions. The sun rotates at its fastest point, at its equator, about once every day, and much more slowly at the higher regions. The way this is mapped out in general is, of course, you can use sunspots if you're not at a sunspot minimum in the cycle, because those sunspots will, betray the motion of the surface. Different size of stars also, and different masses of stars do also show this behavior. They all rotate differentially. And yes, more massive stars tend to have larger angular momentum. They tend to be more rapid rotators, and they tend to have more differential motion, so larger variations between the rotation of their equators and their poles. But it's very hard for us to observe this directly on other stars, except a very couple of nearby supergiants.
The next question is from a variety of participants. It's kind of a conglomeration of questions, but it's basically, how do we know that the universe consists of, they say 78%, but whatever percent of dark energy, since we don't have an instrument to measure it? And how do we measure dark energy, and how do we measure dark matter?
Right. What does this pie chart that we often see of the universe mean, where the three main components of that are about 4% normal matter. That's the stuff we're made of: protons, neutrons, electrons. 24, roughly 24% dark matter, and the rest dark energy, which is the majority. When people make these pie charts and define these things, they're essentially taking the mass energy of each component. Remember that mass and energy are interchangeable or equated by E equals mc squared. So you can say what the equivalent energy of something that has mass is, or what the equivalent mass of something that has energy is. And so this is a currency, mass energy, by which you can do an accounting of the universe. And that's essentially the way it's done. So for the normal matter, which we call baryonic matter, the stuff we're made of, it's easy to say what that is. That's about 10 to the power 80, one with 80 zeros after it, protons and similar particles. That's the mass of the universe. The dark matter, even though we don't know what the particle is or the nature of the dark matter is, we can weigh it. We do know its mass, and we put it to be about 6 times the mass of normal matter. And then the dark energy, in terms of its equivalent mass, if you like, since it's measured as energy causing accelerating expansion, puts it to be 3 times larger than the dark matter and much larger than the normal matter. So that's how the accounting is done.
All right. It's the next question is from an email. Gitanjali would like to know, what is a blitzar?
I'm not sure I know what a blitzar is. There's a blazar, which is something I used to work on. These are active gas. So I'll answer the question. I'm getting echo at the moment.
Oh yeah, sorry. No, I think that's me. So Wikipedia says it's some kind of a star that can rapidly collapse into a black hole. But blazars, I think, we know more about those.
Yeah, let me answer the related question. I don't think a blitzar is a thing necessarily. So a blazar is a very evocative word to define an active galaxy. So this is a supermassive black hole at the center of a normal galaxy that's in a very active state. I worked on blazars for a couple of decades, actually, the first research I did in my thesis, and what I first did when I came to the University of Arizona. The reason they're interesting is that the blazar subpopulation of active galaxies, they're like cousins of quasars, if you like, which are also supermassive black holes that are often inactive for much of the time. When blazars are active, they're about as active as any active galaxy. In other words, they're converting mass into energy through mechanisms near the black hole at a very efficient rate, and they're pumping out enormous amounts of energy in relativistic jets that are moving at large fractions of the speed of light, the plasma in many cases moving at 99.9% of the speed of light. And that energy production is occurring across the electromagnetic spectrum. So blazars are routinely detected at every wavelength from gamma rays out to radio waves. That's like 15 or 17 orders of magnitude in wavelength or energy. So blazars are quite spectacular. And some people have evocatively said that it's like looking down the throat, because you're looking at an object where the relativistic jet is pointed at you, and that gives you a relatively unobscure view onto the supermassive black hole. Is like looking down the throat of a supermassive black hole.
All right. The next question, this I think will be our final question for today, is from Siddharth, who is on with us live, who would like to know, how accurate are the measurements of gravitational waves detected by LIGO, and how do scientists achieve such small measurements?
So it is a remarkable project, the LIGO, Laser Interferometric Gravitational Observatory. First successful in 2015, and now been taking data for 5 years and about to come back with new sensitivity. It is the most sensitive physics experiment ever. The dimensionless figure of merit for LIGO's detections is 1 part in 20 to the 21, 1 part in 10 to the 21, 1 with 21 zeros after it. That is the relative displacement of space-time caused by a gravity wave relative to the size of the detector itself, which is 5-kilometer long arms in 2 different locations in the US. So phenomenally accurate physics experiment, actually thousands of times more accurate than any physics experiments ever. So that's the figure of merit of the sensitivity of LIGO. The actual measurement of the signals is quite reliable because it's an interferometer, so it's looking for very tiny changes in the length of the two orthogonal arms of the interferometer caused by gravity waves passing through the detector and, of course, the Earth and everything else. They travel through solid mass as if it was butter. And these signals are actually quite well detected by LIGO. LIGO has a lot of noise suppression by being in the geologically quiet parts of the United States. There's very clever electronic suppression techniques for taking noise out of the electronics. And so LIGO is, the signals that LIGO has detected in the publications of black hole mergers are based on data that's where the signal is actually very strong. It's very easy to detect. There are going to be signals where LIGO, it will be marginal detections where you would just be unsure whether that is a signal that you can tell comes out of the noise. What helps LIGO in detecting its events is that the signature of mergers of black holes is a very characteristic trace, and you can model the characteristic gravity wave pulse from a merging black hole system in a computer very reliably now with general relativity and so on. And so you can predict what waveform you're trying to detect, and you can use a filter, a matched filter in your instrument to pull that out of the noise. And that gives LIGO its sensitivity, and it's really quite an extraordinary experiment. So that's a good question to end with. Appreciate everything from comets to cosmology. That's the full gamut of the subject this week, and almost most weeks we get through all that. We'll be back next week. We're going to keep it up once a week, different time, different day, and I look forward to having you on board again.